Welcome to the SI lecture series on amendment of fly ash as a construction material for infrastructure development, a life cycle assessment. Dr. Sarat Kumar Das is a professor and head of the Department of Civil Engineering at the Indian Institute of Technology, Indian School of Mines, Dhanbad. He obtained his bachelor degree from CET Bhubaneswar, followed by his master's and PhD in Geotechnical Engineering from Indian Institute of Technology, Kanpur. Supported by the Endeavour Research Fellowship of the Australian Government, he undertook his postdoctoral training at James Cook's University, Australia. He has about 30 years of experience in civil and geotechnical engineering, both in the fronts of academia and industry. His research interests include AI and optimization methods in geotechnical engineering, geoenvironmental engineering, and biogeotechnics. He has published more than 100 technical articles in journals, conference as book chapters, and has supervised 6 doctoral students to completion. He is editorial board member of Environmental Geotechnics ICE and International Journal of Geotechnical Engineering and reviewed more than 60 technical journals. He is a founding co-convener of AGRP lecture series, an ex-executive committee member of the Indian Geotechnical Society and a technical committee member of the International Society for Soil Mechanics and Geotechnical Engineering. He has delivered many invited and distinct keynotes, including a theme lecture on AI methods in the Asian Regional Conference of ISSMGE. Professor Das is my master's as well as my postdoctoral thesis supervisor. Not only me, many of the students, maybe some are present here, always tell the true meaning of research and science we understood under his guidance. So, with this, I welcome my beloved Professor Sarat Kumar Das for the lecture, Characterization and Valorization of Fly Ash.
Thank you, Dr. Surbi, for giving his introduction because you are my student, you are biased. So, good morning and good evening, everybody. So, I am going to present the topic on characterization and valorization of fly ash as a construction material. Is it visible, my slides in presentation mode?
Yes.
Yes. Thank you. So, in the last, yesterday, we had a very good talk from Professor D.N. Singh and Professor Reddy. So they have discussed about that how this fly ash can be utilized in different ways. So here I'll start with again some basic properties of the fly ash which we need to evaluate, and then maybe it will be easier for us to utilize it. So now when I come to this fly ash, I will say you this graph. If you look at this graph, this is about India only. This is latest in 2021 data. So look at the percentage utilization. In 1993-94, it was only, the generation was also very less and the utilization was also limited to 3%. And as you see, as the time grows, the dependency on the thermal power plant in India increased. And then there was a fly ash mission. So after this fly ash mission in early, between 95 and 2000, then its utilization percentage increased. And now, if you'll see the percentage utilization, it is almost 92%. But look at the other aspect. If you will see the generation, so the generation part is also increasing, like from around less than 50 ton to, 50 million ton to now it is 275 million ton. So even if our percentage of utilization has increased, this 8% also accumulates a huge amount of fly ash covering the vast area which could have been usable for other purposes. And by 2031-32, the generation would be 1,000 metric ton. So if we go in this rate, 5% of unutilized fly ash also will have 50 million tons, and that will take huge space. And most of the industries nowadays facing the difficulty of increasing the capacity only because they don't have an answer how to dispose the fly ash or how to utilize the fly ash. This is not the case in India. If you look at the China, they are also, this annual output is at 550 million ton, higher than almost double of our value. And even if they have used in different places, starting from cement, concrete, and so on, still 200 million tons is accumulated every year. So all this is, that is what necessitates that we should go for its study. And this is a new material, so we need to read its different properties. So yesterday there was a question of this Class C and Class F fly ash. This is as per the ASTM standard, which is very simple. That if percentage of alumina, silica, and iron content is more than 70%, then we call it as a Class F fly ash. And in mostly the other way, when we talk about Class C fly ash, there the calcium percent is more than 15%. So what happens? So sometimes people also call it as interchangeably Class F fly ash as low calcium fly ash, Class C fly ash as high calcium fly ash. Then in 2007, this Vasilev and Vasilev further classified these fly ash based on its calcium content and also the iron content, because this is what governs its utilization, because the chemical composition is the basic component which you need to find out if you want to really use it for any specific purpose. For that, if you look at this in this triangular plot, we have got this alkali component, calcium oxide, magnesium oxide, and sodium oxide. And the other one is the iron oxide component. If you'll see this part, acidic component, silica, aluminum, potassium, and tin. So accordingly, they said this side is acidic, this side is basic. And what I have done, I have put around 50-60 fly ash data all around the world. If you'll see, is most of the fly ash in and around is sialic, or it is mostly dominating in aluminosilicate compound. And there are some fly ash also, which we call as high calcium fly ash. They are called also calcialic, because the calcium compound is not very high. It is less than around 30%. If you just compare another industrial waste we call blast furnace slag, the calcium content is more than 35%. So in that comparison, this high calcium fly ash contains calcium oxide varying from 15 to 30%. So as you see this data, so this will tell you also the pH and its huge in future, how these fly ash can be utilized. And then that will also able to get its valorization. So what I said now, we have got two types of fly ash, class F and class C. Then if we go for the origin, mostly class of fly ash are from the bituminous or subbituminous coal, whereas class C fly ash from lignite base. And lignite deposit always very less, so the class C fly ash is very less. And yesterday also, Prof was saying the class C fly ash can be readily used because it's cementitious. Whereas class F fly ash is not cementitious, so it gets accumulated. And then another aspect of this fly ash is morphology. When I want to use this material, so that time I need to know its particle size. Being in geotechnical engineering, we had read all our clay particles are laminar or plate-like structure. Whereas, if you look at this fly ash, this fly ash is a class F fly ash, they are spherical. And the size varies from 1 micron to 100 micron. Because when this coal is burnt around 1200 to 1400 degrees centigrade and immediately cool down, it goes to the air. So this sudden cooling, these droplets are formed as spheres. And this spherical, further also it has been found that this is also hollow. Inside, there is some gas. I'll show you some inside structure also. And that is what they called as a cenosphere. And if you look at another type of that particle, inside there is some structure and this is partly broken. And this, it is denoted as plerosphere. And I will show you now, just look at these two. This is one and this is one. These two particles look same, but this is actually the lunar earth. This is not fly ash. This is my fly ash and this is the lunar soil. So just imagine, if we'll say this fly ash, now we say industrial waste and this particle size food, if we look compare it, it is something looking like a lunar soil. This data I have taken of a paper in, I think, 71. I just could not get the reference, so I could not put that. But this, all these are the lunar soil. So compare this with fly ash. So this is how now we are able to say that this, what we are saying industrial this fly ash has got similar, somewhat similar to condition naturally has also happened somewhere. Then what I try to, as I said, if you see this structure I was saying, which we call as a plerosphere, and that is mostly in the class F fly ash. This fly ash, this is some particles like this or some particle like this. I dissolved it using hydrofluoric acid just to take out its skeleton. This, as I said, internal structure, to look at that, this was how the internal structure is. So that means this cover is a aluminosilicate glass structure. So that's why it dissolved using hydrofluoric acid. And interestingly, others have found out this type of structure in concrete where they have used fly ash as an admixture. So that means with time, this structure will go out and this type of internal structure will come out. And this is also identified and known as mullite. Mullite is another type of mineral which is rich in, aluminosilicate. So these are the crystal structure, and this is the amorphous phase. So this is how the internal structure of a low calcium fly ash is. This is the external structure which you are looking at is looking very smooth. But then there was also a particle which was rough on the surface. Some particles are there which is rough on the surface, unlike these smooth particles. So then we found this is somewhat rich in iron. So that is what is a rough structure on the surface. So this type of particles are there in, as you will see, in low calcium fly ash or class F fly ash. When you go for high calcium fly ash or class C fly ash, then you see the surface is not smooth. And if some of you had attended the studies class of Professor D. N. Singh, he was showing this type of things when there was a accumulation, that was a activation. So these are rich in calcium and aluminum. So these high calcium fly ash are not smooth structures like this. And then when I dissolve it, because this was rich in calcium and aluminum, so I want to dissolve this calcium with this HCl. So what we found, some of the structure were like this. This structure was also top surface were calcium which got dissolved, and some aluminum structure which were there, they remained like that. So this is what we try to find out the morphology of the fly ash to get the importance, because I'll tell you this importance later on. Then the same high calcium fly ash, when I crossed it in a ball mill, if I crossed it, there I was through chemical dissolving, it is through physical. When we cross it, we see their internal structure is different compared to the low calcium fly ash. So this is a navally. So when we treat it, then I break it, and then we found the internal structure is different. Whereas when it was a low calcium fly ash and I cross it, people say sometimes we say also there are layers. This aluminosilicate glass also means layers. And this aluminosilicate is a source of pozzolanic material. And this in layers it is there, and we need to dissolve it. Then only we can get its properties as a pozzolanic material. So this was the importance of going for this morphological study, so that I can know if it is spherical. So that's why in concrete, they call it as a mineral admixture. It increases the workability, because a spherical will not take more water, but it can make it more workable. And if you will see this picture, and this high calcium plus is reactive, because this calcium is on the surface, it will react immediately. And if you will see this pozzolanic part, this pozzolanic part is on the surface of this fly ash and low calcium fly ash. So if I create such alkali condition, it can react. So all this tells the importance of this morphological study. Then when I said, I want to look at the chemistry of each particle, then we need to go for some other investigation that is called particle chemistry. And that is, we can do with EDX or EDS. So that is electron dispersive X-ray. So using that, any individual particle or a particular location, you can get its chemistry. So this way, how we could identify that this surface is rich in aluminosilicate, or this surface was rich in iron. So this is what we call it EDX. Most of the cases, when you go for this morphology, with this scanning electron microscope, which now it is very common, or its other form is called FEACM, which is further sophisticated, and that is also used for the morphology. But then in some of the equipments I found, if it is not attached with this EDS or EDX, then it will be difficult to say that this particle is rich in aluminosilicate or some other material. So when we are going for this material morphological characteristic, keep in mind, you should always go simultaneously with this the particle chemistry analysis through this EDS or EDX. That is an essential aspect when you go for morphological study, because some of the equipments may not have this EDS or EDX. So taking only morphological study without its chemistry has no meaning. I mean, it can go to only give some indicative, but it's not conclusive. I can't say no meaning, but it indicative, but not conclusive. Next. That other aspect is mineralogy. Because mineralogy plays a big role. We say pozzolan. Which is pozzolan? That is which is amorphous. So mineralogy defines whether a material is, what are the minerals it contains, and another thing it also says what is the amorphous, or what is the quantitative aspect or part, that is what is called amorphous phase. So qualitatively, mineralogy can tell you what are the minerals available, and quantitatively it will say how much of glassy phase they are in. So that's why we need to study the mineralogy. If the glass content is more, that material we call it as a pozzolanic. Not that simply it is aluminum oxide plus silicon oxide, which constitute the amorphous phase. Because part of it may be crystalline, part of it may be amorphous. So as if we say pozzolanic material, because we say Portland pozzolanic cement. So that way, if they take fly ash, they don't take bottom ash. Because fly ash is more amorphous compared to the bottom ash. Because most of you might have heard about this fly ash collected through electrostatic precipitator, which goes or flies out, whereas the bottom ash is the heavier ash part, which they collected in the bottom. So that's why all the cement industry will take only fly ash. They will not go for this bottom ash. That's the reason, because they need amorphous part. They don't need this crystalline part. So here I have shown you two parts. One we call it as a class F fly ash or low calcium fly ash. And here I have just compared two fly ash. One is class C, other is class F. When I say navely, it is class C, and when it is punky, it is class F. So if this is also class F. So if in the class F fly ash, it is mostly quartz, mullite, I was saying glass-like structure, iron is there, so it's maybe magnetite and hematite, but this percentage is less. But mostly it is quartz and mullite. Whereas if you go to class C fly ash, it may contain some calcium silicate or calcium silicate anhydrides or calcium aluminate. So these, if you remember, these type of crystals or minerals are there also in cement. So which makes this class C fly ash cementitous. So itself it has some cementing properties, binding properties. Whereas class F soil does not have these binding properties because it does not contain this type of minerals. This is the qualitative assessment. Then there is another one which we call as a quantitative assessment. I'll go with first this one. So if we'll go to this, what we say, as I am drawing an X-ray diffraction analysis of these fly ash, this is a low calcium fly ash. These are the identification. Suppose this is a quartz and this is molite and so on. But another aspect, if you look at the spectra, there is a hump-like structure. This hump-like structure tells you about the type of glassy phase or quantity of the glassy phase. So this mostly indicates that the type. And as it goes more, so it tells that the more glassy phase is there. So this is around, suppose say here, this value is 22.5 degree. And then I'm next showing you this comparison with the class A fly ash. So in the class C fly ash, class A fly ash, it was suppose say 22, and this is suppose say up to 24 and so on. Whereas in the high calcium fly ash, if you look at this hop position shifts around 29 to 32, 33. Within that, this hop position changes. So this is an also indicative of the quality of the glass. So there is always a difference between the low calcium and high calcium fly ash, or class C and class A fly ash. And this, we call it as calcium aluminate glass, and this is aluminosilicate type of glass. So this is a pozzolanic type of glass, and this is also somewhat cementitious type of glass, glassy phase. So this is what difference is. Then what I did, I tried to take this class C fly ash, which was a naval fly ash, high calcium fly ash, and try to see through segregation. Because many a time it says cement industry, they grind it, or what they show, they take around less than 45 or at least less than 75 micron. What we found in this high calcium fly ash, as I am going less than 45 micron fly ash, those minerals which are cementitious, they are abundantly available. Whereas when I am going above 150 micron, mostly it is as good as class A fly ash. So that means those calcium aluminate part is in the fine fraction. So that way, if this fine fraction will be taken, it will be more cementitious compared to if I take it as a combined proportion. And yesterday also there was something on infrared, like if to identify this glassy phase, as I said, glassy phase here it is indicative, but crystalline phase, exactly it can say that is a quartz. So to further establish that this zone contains calcium aluminum type of glass, or in low calcium fly ash it is aluminosilicate type of glass, this is possible through infrared spectroscopy, that is infrared spectroscopy, which tells that what type of bond it is, whether the bond is SiO2 bond or CaO bond. So that time I will be able to, we can guess what is the type of glassy phase it is. So keep in mind, if excited gives the crystalline phase, infrared will tell you in general the chemistry of it, including crystalline and amorphous, and this glassy phase can be captured through this infrared spectroscopy. So that way, we need to characterize this, what is the, depending upon the type of fly ash and its total mineralogy. As I said, there could be also the variation in mineralogy with the particle size. At this point also, I'll tell you one thing, that this fly ash also contains one more, that is what we call as unburnt coal, because some part of the coal still are not burnt in the plant, and they just came out as it is, what we call it as a loss and ignition. So whenever in a fly ash chemistry, we find something is written LOI, that is called as loss in ignition. This is also another aspect which plays a big role in its utilization. Before 2000, there was a restriction on LOI up to 12%. But then what happened? This was creating a hurdle in the sense, I'll tell you later on how it is going to affect my geotechnical properties and other properties. So then the stipulation or the mandate came that it cannot more than 2%. And nowadays, people are getting loss on ignition because the plant efficiency is increasing, still less. Because the loss on ignition depends upon the efficiency of the plant, and this aspect, it is not in the ASTM standard. It is simply mentioned that was the limit, but its impact is more, and I'll show you later on some of its impact. So loss and ignition, which is nothing but your unburnt carbon. Okay, so when I was telling this glassy phase, so always we normalize with this loss and ignition, we'll remove that loss and ignition because that is never part of any pozzolanic properties. So as I said you, if I want to find out qualitative assessment, I need to know where is the humps, and then this is what I tried to plot it, taking a clue from another previous researcher. So they were thinking that based on this line content, there is maybe increased change in hump position. So if we'll see, this line content, as I was saying, more than 15%. So the hump position starting from 25, it goes up to, here, up to 32, 33, if it is more than 20%. So if it is up to 15 or so, then there is a gap. So then there is a gap, and then beyond 20, if you'll see it's 32 and so on. And here also GGVS or blast furnace slag lies in this zone. Then that is qualitative. As I said, the type depending upon the calcium oxide, the qualitative of the glass from changes this to this, aluminum silicate to calcium aluminate type. But to quantify it, then again, we found a ratio called potassium content by aluminum content normalized with its molecular weight. Then there is a linear relationship between the glass content. That means this is qualitative and this is quantitative. And the glass content more means better flyers. So based on this, so data is from different. Actually, this is the first. They try to give this type of correlation. Then later on, I have added so many other data points, and if you'll see, this is within 12% error. Most of the points lies. But then I found it could be better if I can divide into three types of or three groups of flyers. So it's not that this ratio only which is responsible to tell you the pozzolanic or amorphous phase quantity, rather there is something else which at the same ratio of K/10, which was suggested by Howard et al., that further we say that there is some other thing which is playing a role, and that could be mostly the efficiency of the plant, that is your grinding and so on. And these data only I can say you the limitation is I have not added very recent data after 2015 or so. So this data previously it was there whatever has published, but starting from 1950s. So all these data points where, because getting the information about the glass content, measurement for the fly ash is very limited. So whatever it is possible around more than 50 data, that is what I have plotted here. So as you say here, so that is also important to know from the chemistry, what is the amount of glass content. So that's why you need to go for this chemistry, morphology, and mineralogy. So then this is finally, it will tell you what is the pozzolanic behavior, where it is therein. And that is also, I didn't show it here, but that based on that also I have given a correlation to find out a properties, how you can predict the compressive strength of motor using fly ash. The data is historical database, but using this information only I have tried to make a statistical plot. Anyway, so that I will not put it here. Now I am coming to as a fill and embankment material to make it going towards the geotechnical aspect. Then here again, as I go for geotechnical aspect, we are talking about two, what we call it as a class A fly ash and other is class C fly ash. So this is your C and this is your C, the other two are F class F fly ash. All you know about this hydrometer analysis we do for the fly ash. But as I said, class C fly ash on the surface itself, there is calcium aluminum type of chemicals. So it is going to immediately react. So in the hydrometer, if we do it, we may not get the proper result. So we can go with some other liquid, and that using the other bipolar liquid, the method we call it as a Coulter counted or this laser diffraction method you can use to measure the particle size distribution. That distribution will give in volumetric proportion and you can convert it to the gravimetric. But again, I'll say you, there may be an error because all these particles are not of equal specific gravity or density. But still you can get an approximate value. So this, if you are going for class C fly ash, you should go with this one. Otherwise, you may not got the true grain size distribution of the fly ash. Even you look at the compressibility, how quickly it reacts. So if you go with class C, that is a cementitious, hardly there is any change in void ratio. But if I am going for class F, so obviously I expect rearrangement or pore pressure distribution through which we can go for the compressibility of the fly ash. So this also indicates that class C fly ash immediately reacts, which is called as also, I'll go tell you that what is called as self-hardening properties. Then, as I was saying, it contains different type of material. And the specific gravity as a whole, when we are measuring for the fly ash, as we do the bulk, that specific gravity value varies from approximately 1.9 to 2.9 of a fly ash. So that is a wide variation in specific gravity, though most of the, you see, this is a big chunk. I mean, that is the maximum proportion of the fly ash in this region, but you can have specific gravity here or also could be specific gravity value here. So these contents, we found that higher amount of iron. So if as I was saying on the surface, there is some iron, hematite, magnetite, the chemical. So that way, look at this, that iron content also plays a role and in terms of in your specific gravity. And now if we'll plot the maximum dry density versus OMC, we have got, this is suppose I could have put more points, but just for showing you the soil, if this is the plot, and this is where the fly ash is. The maximum dry density value of the fly ash is less than that of the soil. because the specific gravity is low in comparison to that of soil, most of the fly ash, though it has some fly ash which are but higher. Like here, this high calcium fly ash which I had taken, and this is from, and interestingly, this is this fly ash from India, this is fly ash from Thailand. Mymo fly ash from Thailand. So both this fly ash is high calcium fly ash, and interestingly, they had also somewhat higher iron content compared to the class F fly ash. So what we say, this fly ash is a lightweight material compared to that of soil. Then when you want to go for this fill and embankment material, we always check with OMC and MDD. That is a quality control. But look at the data. If here, suppose say this data same from Kanpur, Panki, over a gap of 2 years. So MDD value changed, so also OMDD value changed. So OMC and MDD, this is the range in a matter of 2 years. Whereas the fly ash from other parts of the world over a different period of time also showed similar variation. This has been also observed. The properties of the fly ash is highly variable, not in terms of only the type of coal. With coal, every day they get it. The processing and the plant efficiency. Finally, even the load, at what capacity the plant is operating, how much power it is generating. Now people have found also that make a difference, but that information I don't have. But they have not done for geotechnical investigation, but for other investigation, they have found there is a difference, even in the load fluctuation in the thermal power plant. So this quality control aspect is very important when you are using fly ash as a geotechnical material. This is another interesting plot. What I did, as I was compacting, I was doing this OMC-MDD at each moisture content, I was taking its UCS value, unconfined compressive strength value. So this is for Panki, this is F fly ash, this is class C fly ash, this is also class F fly ash. But the problem is here, if we look at this and this, there is a variation. And obviously, class C fly ash has got higher unconfined compressive strength, vary as a log scale. If it is in terms of 0.2, it is 1.1. So in MPa, megapascal. So that is around 10 times, or suppose say 8 to 10 times higher values. Then what I did, I want to check its strength. If you see closely, based on this, this is a dry up optimum, weight up optimum, that is one. And then this is at OMC. Then I put it inside the desiccator where there is less chances of or very less moisture loss. Whereas another case, I just put outside the desiccator. There will be moisture loss from the fly ash. So this is moisture loss from the fly ash. So look at this. So where I was continuing. So you see, if it is kept outside, as it lose moisture, so strength suddenly decreases. So that's why what we get the strength or that question, we can call it as apparent question. So that's why all the fly ash fields, what you will see, they cover it. They cannot keep it exposed to the outside. This is the reason, because if it loses moisture, it it will lose its strength and it will have almost zero strength. So that is what I was saying, that when I say calcium aluminate type and aluminosilicate type. Its class F fly ash also contains certain amount of calcium oxide. And that is what gives it to the strength called self-hardening properties. So I want to differentiate between self-hardening and pozzolanic strength. So self-hardening properties is which without any additive or without any cemented properties, it can have certain strength. And if you look at this one, these are all high calcium fly ash. This is from Thailand, this is from India. The strength is more than 20 MPa, unconfined strength. And this is with time, this is after weeks. So after 4 weeks, if you see, the strength is almost 20 MPa. Whereas in this, even if we'll show as this most that what I'll say calcium oxide increases, can maximum go to 3 to 4 MPa. These are class F fly ash. Even if they have got 5 to 6% of calcium oxide, but there the mineralogy is different, so the self-hardening property is less. But in contrary, if we go to that, when I talk about the pozzolanic strength, so this side, this is the strength without any cementitious material. As I put the cemented material, then immediately it increases. So that is what we call it as a pozzolanic strength or pozzolanic value. So now, after telling about this as a fill and impact material, I want to tell you one more type of material where this fly ash can be used. So that is what we call it as a control low strength material. So in this, where we use it, look at this one. Many times we fill it. We cannot compact the soil when you fill it because we have got some underground facilities. Rather, you can make it like a slurry and fill it with. So in that case, this is what we need to study the properties. And here the fly ash plays a very big and important role. Because as I said, the particles are spherical. As these particles are spherical, so it increases the workability, and in fact, it acts like a mineral admixture. So for which any control low strength material, if possible, we try to use fly ash. Fly ash is almost an essential part of this ideal control low strength material. So there, like here, we have done one with coal mine overburden and this fly ash. We need to calculate the flow value that we found within the limit. And the severe value can go beyond 140 or 180, around 180. The UCS value can go up to 3 MPa. So it can work as a very good fill material, structural fill material, which can really take the load. So there we can use the fly ash instead of simply using fly ash as a fill material. If we add it here, then its validation or the importance gets increases. But when we go for this type of material, this is a highly heterogeneous. We need to do certain types of test, like your flow for this bleeding. And then also we need to find out the strength and its durability, and also this porosity, how it is, because there you don't compact it, then how much pore space inside through ultrasonic pulse velocity, or we can also check its water absorption. And finally, when we dump it, if there is any depression in it or not, when I fill it, because this is no compaction in this material, only simply I make it like a flowable fill and leave it. So that it's a self-compacting, it's just like a self-compacting concrete, it's self-compacting soil admixture. So this I will not touch. Okay. So this is how we can check also the flowability. One more thing I'll go for where we can use fly ash is called alkali activated material. As it is a fill, the valuation is low valuation. If you are using suppose a CLSM, it can have higher valuation or sorry, medium valorization. Then when I go for cement concrete, high valorization. See, in the cementitious material, another type of cementary material is coming, which is called as a geopolymer. There also, because of its pozzolanic properties, the fly ash can be used as an alternative to natural pozzolana. Because what we call it a geopolymer may be new to some of the person. This is an alternate cementitious material. And in case of, if you compare to the Portland cement, which is rich in calcium, this is different, which is rich in other metal, alumina, and this is alumina, and this is what we call it as a silicate or hydrates. So this type of alkali activated material, they found it is more sustainable in terms of greenhouse gas emission. Environmentally, it's better. And there we can use this fly ash as a percussor and this sodium hydroxide or sodium silicate as the activator. Yesterday, Professor Singh was talking about thermal activation. Here we are talking about alkali activation, adding some alkalis, and these alkalis mostly we add this sodium hydroxide or potassium hydroxide, aluminum sodium silicate or potassium silicate. So this is what type of cementitious blocks. If you look at this, it is very difficult to say that no cement has been used in this block. This block, there is no cement, only fly ash, some GGBs, and coal mine overburden or iron ore tailings, which has been used to make this cementitious block. So with this, I will come to conclusion. So if you'll see, coal is still the main source of energy in the developing and underdeveloped countries. And as we say, in India also, it will be around 1,000 million ton by 2031-32. Even if we were able to achieve more than 90% of utilization, still that 8% is also a big volume which needs to be managed. If the fly ash can be properly characterized, so it could be a potential construction material, because the chemical composition of fly ash is almost similar to like that of soil, but its property is highly variable and it depends upon so many other factors. We need to have a good quality control or regular quality control. And this can be used in different low value, medium value, and high value utilization. And for this, what Professor Reddy was yesterday talking about, you can do life cycle assessment analysis for different types of product to find out its environmental impact. So that's why I tried to not present here, because I tried to focus more on the characterization. And still more research is required to, if you want to go for increase or go for its high value utilization. Thank you. So I say always, ignorance about anything makes it as a waste. But once we have knowledge about it, it will be, we'll call it as a wealth. So that's why that means we need to gain still more knowledge about this fly ash. Then fly ash will never be waste. It will be just wealth. Thank you. I'll be
Thank
happy if you have got any question.
Yes, sir. Thank you. Thank you, sir. It's always new whenever I hear you. Uh, First of all, I want to give the attention like this all characterization he have done maybe in the year of 2005 or 6, which got published in 2 papers, and I have already sent the link of the papers in the chat box. Whoever wants to know about more on the characterization of fly ash, they can go through the papers. And here are the questions. One from Malay Chetia. What is the simplest method to identify whether a fly ash is class F or class C type?
Okay, that means as I said, this is the first initially, as you said, the chemical composition. But if you cannot do that chemical composition also, still, if you'll go for just a minute, let me share it. Okay, so as a engineer always, it's not possible to go for the detailed chemical characterization, but simply a pH measurement also will indicate you, because that's why in the chemical characterization, what I was saying, that which is sialic or acidic and so on. Just a minute, I want to share that. Say, is it visible?
Yes, sir.
Yes, you
Yes.
see here. If you look at this, so it will be acidic. The pH value, it may not be less than 7, but very close to 7. Whereas in high calcium fly ash, it will be always more than 7. So it is a very, I'll say the most simplest method you can go for by simply taking the pH value. So if it is acidic, it will be class A fly ash. If it is basic, then it will be class C fly ash.
Yes.
Yes, please.
The next question is from Dr. Brahmadev Yadav. In liner design, which type of fly ash is more useful, class C or class F? And can you explain more on the quartz and mullite component of the fly ash?
So as Professor Reddy was also started talking about, class C fly ash is very less, because if you think about India, lignite deposit is in Tamil Nadu and in some part of Kashmir, Srinagar. I mean that, sorry, not Srinagar, Kashmir area. So we have very less amount of class C fly ash. If you, in terms of its cemented process, obviously people will tempted to use class C fly ash, but that's not the challenge. The challenge is how to use the class A fly ash. Class C fly ash, we still want to increase its valorization. Its production is very less.
Yes. And the presence of the quartz and mullite in the fly ash.
Yes, quartz and mullite is because of its chemical composition. If you see the chemical composition of the fly ash, it mostly contains alumina and silica. So this alumina silica is, which obviously in mineral form we call it as a quartz and mullite. This mullite also I have shown you the lat-like structure. So this mullite, if you see, it is a lat-like structure which is rich of aluminosilicate, but more of alumina. But if it is more of only silica, so we call it as a quartz. And these are not easily, it cannot be easily dissolved. So that's why it is not very reactive. Only when it is in amorphous phase, these are reactive. That's why we call it as a pozzolana. This natural pozzolana, which obviously, you know, that is coming from the volcanoes outside. And this is similar to from high temperature, it cools down to low temperature in a very sudden time, but still some of this also get crystallized. So that is what we call it as a mullite. The other wheat part, get it cooled quickly, that is becomes amorphous, which is on the surface of it. And that is the pozzolanic part. This part will not react in cement or whatever you add it, lime or cement.
Yes. The last question. The LOI should be less or more for seepage control design?
LOI has got, because he's maybe in thinking of that seepage control means to reduce the seepage, it will not absorb how much it will absorb. So this LOI is in a very fine particle, less than maybe less around a micron or maybe maximum up to 10 to 20 micron, because it has been crushed, the coal has been crushed. So that itself is not going to stop your seepage. And this, in fact, once these are light materials, most of the time when we put it in a slurry form, it comes to the surface. So in that aspect, this can never be a beneficial effect in geotechnical properties. So it is better to avoid, and most of the plants are now with less than 2%. And that is why only we call it as there is also another aspect, what you call as a high ash content fly ash or low ash content fly ash. So when our Indian fly ash, Indian coal has content almost 40% ash content. Well, that's why we import some other coal from other countries, mix it and do it in a thermal power plant to reduce this LOI content. Okay, thank you.
Thank you, sir. We don't have any more questions, but whoever have any doubts on fly ash characterization, they can reach Professor Sarat Das via mail. Thank you, sir. I still remember when I asked you, like, okay, sir, 90% our fly ash is already used. Why we are asking, like, why we are trying to still use the fly ash, why we are writing some of the proposals. I still remember the answer, like, though 90% we are utilizing, the 10%, the quantity is much more than the production of other mine waste or other industrial waste. Yes.
Yes,
Yeah.
that is the other industrial waste still less. The total amount is less than that. What is the unutilized fly ash? Yes, Dr. Somi is already waiting. So, so now, can we use fly ash as a full substitute the cement? No, and that is possible only through alkali activation, what is called geopolymerization. So in that, Dr. Sumi, just 1 minute I'll take to answer his question. So that way, now people are trying to use it like through alkali activation, this fly ash and the sodium hydroxide, potassium hydroxide, sodium silicate, potassium silicate, they are adding to make it a cementitious material. In that case, it is 100% fly ash. So that way you can say that it is possible to use fly ash as a cementitious material through alkali activation.
And I think otherwise that is known as third stage or some stage of like
third generation cement.
Third generation cement.
Yes, which is more sustainable. It does not, it's a greenhouse gas impact is less, but still energy impact to get that chemical is not sorted out. And bulk utilization is not yet proved. And there is also the problem with efflorescence and other. So that's why still it is in the laboratory yet to get really utilization in the professional field.
Okay.
Thank you.
Thank you. Thank you, sir.